Good morning to all, and thank you for this opportunity. It's really a pleasure to be here. And before starting, I want to thank all my team group and especially Laura Poletti for her very big work, and Silvio D'Avolio of ISAC CNR for sharing his knowledge of numerical weather prediction system and for his collaboration. So let's start, and very two words about motivation, similarly to what say the Maria Helena region, which is Liguria region in the northwest of Italy, is located in Mediterranean environment, and which is struck by very intense rainfall events, which in many times occur only on small portion of territory, and a territory which is made by a collection of small and very small catchments. So in this context, we believe nowcasting is quite important for hydrological application. But we know the limits of nowcasting. We talk of nowcasting the algorithm based on the recent observation, and we know that the physics generally is not well represented. So growth and decay of precipitation structure cannot be described with high reliability. So we need to connect nowcasting to meteorological models which describe the physics of the processes. And in fact, we developed is similar to the one is based on the use of nowcasting algorithm and the blending system to blend the precipitation derived by nowcasting system to numerical weather prediction systems. And the target, so the objective is to generate forecast rainfall fields with the duration of about 6 hours and a frequent update trying to exploit the new observation that are available. These rainfall fields are used as input to a hydrological model to generate and produce a hydrological forecast in terms of stream flows. So the elements of are various. The first is FAST, which is the stochastic nowcasting system. Based on it used as input the last observation derived from the radar systems. So rainfall fields with a spatial resolution of 1 kilometer and a temporal resolution of 5-10 minutes. Then through a Fourier transformation, we go to the spectral and phase velocity spaces. So in the model, the spectral amplitudes are kept constant, and this is a limit of the model, but because this means that the total volume of precipitation is constant along the forecast, while the phase velocities are evolved. Each scale is evolved with different velocities. This allow to combine different scale and to forecast the different scales with their velocities. Then we come back in the physical space and we generate a rainfall ensemble because this system has a stochastic terms, and so we have an ensemble of all possible rainfall scenarios. The other element is the numerical weather prediction system, is MOLOC, which is developed by ISAC CNR, which explicitly solves the deep convection. And in this application has a spatial resolution of 2.2 kilometers and we applied a data simulation technique, quite simple data simulation technique, which is nudging, and the model-specific humidity is progressively modified depending on the observation of precipitation. So with high frequency, which is 1 hour, the model is modified with the recent observation. And the result is a deterministic forecast, so one rainfall field forecast for the following hours. The other element of the model, this is continuum, which is a continuous hydrological model. This allows it to begin the simulation using the real state variable of the model, derived from what happened the days and the weeks before the events. And the interesting thing of this model, as many other models, which is distributed. So this allows to evaluate the variable, especially stream flow, in each grid of the calculation, in each cell of the calculation grid. The blended technique. The blended technique is made by two steps. The first step is a modification of the nowcasting model of the nowcasting rainfall fields using the volume trend, the precipitation volume trend derived by the numerical weather prediction system. The numerical weather prediction system is frequently hourly corrected with the observation, and then the forecast, the new forecast is used in the first step to derive a percentage trend of the volume in the following hours, and this volume trend is applied to the nowcasted rainfall feeds derived by the nowcasting system. This allows in such a way to overcome the problem of the constants of the volume of the original nowcasting model. The other step of the blended technique is quite common, is a sort of linear combination of the fields derived by nowcasting and derived by the numerical weather prediction system. The difference is that since we applied the first step of the blending technique, the weight given to the nowcasted and corrected fields is generally quite high for the first 1-2 hours, so very close to 1. And then there is the decreasing of the function until 4 or 5 hours of lead time. And after this lead time, all the weight is given to the numerical weather prediction system. In this application, we applied all the framework every 20 minutes. We could also go to 10 minutes because radar data are available every 10 minutes. But we try to, in such a way, reproduce an operational system where we need some computational time to have result, and especially regarding numerical weather prediction system, and which is updated every 60 minutes. And so it needs to be run again every 6 minutes. We gone to some results. We compare 3 configurations basically. So the first configuration is using the original nowcasting system, so with the hypothesis of constants of volume, of precipitation volumes along the forecast. We used in this exercise the nowcasting model to forecast 6 hours of precipitation. We do not do this choice in operational application because we know that the reliability is very, very low after 1-2 hours. The second configuration is the application of first step of the blending. So only the correction of the volume in the nowcasting system, and the third configuration is the complete chain, so step 1 and step 2 of the blending system. It is evident that when we go to the complete configuration, the variance of the stream flow prediction decreases with lead time, because we are combining a probabilistic forecast, so probabilistic input to hydrological model with the deterministic one. So when the weight of the numerical weather prediction system comes and is close to 1, the hydrological forecasts tend to be deterministic. We carried out 2 types of analysis. One, we can say standard point analysis, so choosing some sections as reference sections and calculating some scores that you see on the right, and Southcliffe, variance, and reduce continuous rank probability score that I will call it RCRPS. Then we carried out a distributed analysis, so putting together the results in all the grid cell of the model. We use a threshold on the area, so we consider all the grid cell with the area larger than 15 square kilometers. First case study, we applied all these to 3 case studies. For sake of brevity, I will present 2 case studies. The first is the October 2014. In this case, the results are not so fantastic. In terms of Nash Southcliffe, we can say that results are really similar in the 3-4 configuration. We present 4 configuration because we consider in this graph 2 blending function, different blending function. We can see that variance in using the complete blending configuration increases for the first hour, because there is the presence of the probabilistic forecast driven by nowcasting system, then decreases because the forecast becomes deterministic. Then we plot the box plot of RCRPS, and in this case we can say that well, the results are not so different, and sometimes using the original nowcasting system is better, but or a little bit better. There is a reason for this. This was a particular event where the rainfall hit a particular area of the area. So in this case, the constants of the volume was a good choice, and sometimes can do better than the use of numerical weather prediction system. This is confirmed by the distributed analysis. In this case, we put together all the results of all grid cells, and we classified them in 3 range of drainage areas. So we have very small, and we can say large basins. And again, we see that results are a little bit better, especially for larger basins, in the case of using the nowcasting system, the original nowcasting system, or the nowcasting system with the correction of the values. If we move to the little bit, we can say that from the analysis, the point analysis, the Nash Southcliffe is not very different from a configuration to another, but we can see that with increasing lead time, the RCRPS improves. And this is, in our opinion, good results. Clearly, at the beginning for the first lead times, the results are really similar because input is really similar. And then when we go on with lead time, results improves for the two configuration with the complete blending system. Again, is confirmed also by distributed analysis. There is an improvement in terms of RCRPS for the different range of drainage area in the pixel, and especially for larger basin in this case. The third event that I don't show is the results are really similar to this one, so this is a good result in our opinion. What are we doing now? Is to set up, to improve the setup, to improve the system, but to make a setup at national scale in Italy. So we already have the nowcasting model, which is running on national mosaic of radar data, and this is pre-operational and working in real time. We are setting up a version of the numerical weather prediction system WRF with the 3D VAR assimilation system, which should be a little bit more sophisticated than the simple nudging, and we will assimilate radar reflectivity, ground data, and probably also some satellite data. And then the third element is a national scale hydrological model, which is already running, is currently operational for civil protection purposes. So we will try to extend the area of application and modifying some of the elements of the chain. So to go to conclusion, we believe that using an integrated nowcasting system can be useful in real time to have an idea of what is going to happen, even if, as also shown by other presentation, not always the exact magnitude of the event is captured, is forecasted, but many times, in many cases, when for civil protection actions, we have to have an idea if we will have a very strong event that will carry out damages and problems to population. The use of best rainfall forecast obtained by combination of nowcasting and numerical weather prediction system is useful. Even in some particular situation is not so different by using nowcasting, at least for the first 6 hours of prediction. Some interesting case and that critical case are isolated thunderstorms, which in many cases are difficult to be predicted also with the sophisticated numerical weather prediction system. And certainly the blending technique is useful, but sometimes there are problems when the numerical weather prediction system is quite different from recent observation, and so from the first hour of nowcasting. So it seems to be, we can say that maybe it is not mandatory, as I wrote in the presentation, but we believe that it is useful to apply data simulation techniques on the numerical weather prediction system to drive the numerical weather prediction system to reproduce the observation as much as possible. Finally, possible problems in an operational perspective are related to calculation time, which is in this case are quite negligible for FAST, which is nowcasting system, but as you know maybe better than me, are not negligible for numerical weather prediction systems. So in an operational perspective, this could be a problem. Supercomputer could be helpful, but it's element to account for. That's all. This is my presentation, and thank you all.
Thank you very much, Francesco. I'll start by a question here from Clemens Zimmer. He's in University of Bonn. Can you give more information about the nature of the national scale hydrological model mentioned at the end of your talk, please?
Okay. It is implemented at spatial resolution, which is a little bit less than 500 meters. And it works with the hourly time scale. The run is in the current configuration. The run is updated every hour. So every hour we get new information from radar network and also re-engaged network, national network. So we merged the input in a unique rainfall input, and then we use input for other variables needed by the model, which are temperature, wind velocity, and so on, by the ground data. And this is more or less the summary of the implementation at the national scale.
Okay, thank you. Any more questions here in the speakers room?
I have a question.
Yes, please.
From Marco. Thank you, Francesco.
Hi, Marco.
I wonder if you have, if it is possible for you to evaluate the lower aggregation scale where the accuracy of the nowcasting and meteorological model chain you have presented is failing to provide a good forecast. If there is a lower threshold for the aggregation scale, spatial aggregation scale.
Aggregation scale. This is a good question in the sense that for my experience, for the experience that we carried out in this year and for this project, for this work, is that depends on the events. In some cases, we have a quite high accuracy also for basing that we can say have a drainage area of 20, 40, 50 square kilometers. In some other case, the system fails and move precipitation some kilometers far from the reality and hits other basins. But I think that in many cases depends on the type of the event, especially when we have isolated thunderstorm. Sometimes it's really difficult to predict precipitation far from 1 hour, 2 hours. Even a numerical weather prediction system, I don't have here the slide, but there was a very interesting case where we use the system for another event, and the event was in his general magnitude very good predictly. The prediction was good because the structure of the precipitation was good, but it was 20 kilometers moved far from the reality. So the event was predicted, but it was predicted in another place. And if you want to go to the scale of very small catchment, it could be a problem. If we want to have an idea of what is going to happen in a region, in a quite large region, this is good, okay? It depends on the events and depends on your target of the of what you want to obtain.
Thank you very much, Francesco.
Okay, thank you very much. We have other questions, but I propose to go for a very quick coffee break now so that we can stop being late with our schedule. And so I'll see you all back at 11 for the presentation of Linda Spite from Reading University. Okay, thank you very much for all.
Thank you. Bye.
Bye.